Hello, calculus friends. Today we are going to talk about how to do what I like to call advanced partial fractions. So, if you've taken BC calculus, we do very simple partial fractions, but they get so much bigger and so much more fun that we're going to look at them some more. So, a partial fraction is one of those things where you take a fraction that's got a big denominator, and break it up into fractions with smaller denominators. So, I'm calling example one your basic, typical partial fraction. And if we look at it, what we can realize is that this denominator right here will factor into x minus 7x plus 2. And I'm going to leave my numerator alone. So if I have a denominator that is basically a composite, that's a product of two things, I can break up into two smaller fractions. Those fractions are going to be a over x minus 7 plus b over x plus 2, where a and b are constants. And if I add those fractions together, I want to get the one that we have, which is 3x minus 4 over x plus 7, x minus 7x plus 2. Now, in order for those to add together, they would need to get a common denominator. So my a fraction would be multiplied by x plus 2 on the top and the bottom, and the b fraction would be multiplied by x minus 7 on the top and the bottom. And so I do that, and I get ax plus 2a plus bx minus 7b all over x plus 2x minus 7, and that should still equal 3x minus 4 over x minus 7x plus 2. And now I have an equation where the denominators match, so I can ignore the denominators. And then I can use the numerators to make a system of equations. I have ax's plus bx's for a grand total of 3x's. So then I know that a plus b is 3. I have 2a as a constant minus 7b as a constant equals negative 4 as a constant. So I know that 2a minus 7b equals negative 4. And lucky for us, these are stacked very nicely as a system of equations that I can use elimination on. So I am going to multiply this top equation by 7 and then add the two equations together. So 7a plus 2a is 9a. 7b minus 7b is 0. 7 times 3 is 21. 21 minus 4 is 17. And then I'm going to divide by 9 and get a equals 17 ninths. Okay, fine. Then what do I want to do next? Well, let's see. I also know that a plus b equals 3. So b, 17 ninths plus 10 ninths would be 27 ninths. So that would be 3. And so then I have just figured out that integrating this original rational expression here, would be the same as integrating 17 ninths over x minus 7 plus 10 ninths over x plus 2. And the reason I like that is because I didn't know the antiderivative of the first one. There's no rule for integrating something like that. There is a rule, however, for integrating something where you have a constant over a linear. And that's your ln rule. If I did a u sub, you could see it that way, but this is just going to be an ln. The antiderivative of 17 ninths over x minus 7 is 17 ninths ln absolute value x minus 7 plus 10 ninths ln absolute value of x plus 2 plus c. And there you go. The other thing I'm going to spend time doing here is I'm going to open my computer back up and show you how you can check your answers. Because one of the best things about taking these antiderivatives is that you can check your answers. Now, there's a couple of ways that we could do this. Option one is we could go over here to Wolfram Alpha. Can you tell I've typed in Wolfram Alpha before? It pops right up. All right, what do I want to know about? I want to integrate, let's see, what was I integrating? 3x minus 4 over x squared, what was it? Minus 5x minus 14. And then if I hit equals, it should do this for me. Complete input. It doesn't like this. It's just being slow, apparently. Come on. You can do it. Oh, I think I have to do this. I don't know what's going on here. Let's try this again. Ah, finally. Finally. 17 ninths log 7 minus x plus 10 ninths log x plus 2. And if you're thinking, wait a minute, that says 7 minus x, ours says x minus 7. That says log instead of ln. Internationally, log is the same as ln. And since we're taking the absolute value of x minus 7, that's the same as 7 minus x if I were to absolute value both of them. So this works. There's option 1, but that took a really long time. So I'm going to try Desmos and show you another way to check your answer. So if I go into Desmos and go to the graphing calculator, what I am going to do in here is I am going to call f of x the thing that I got. 17 ninths ln, and now absolute value. I think I've got to use, there we go, absolute value x minus 7 plus 10 ninths ln absolute value of x plus 2. There's f of x. There's my function. And I think that it just wants a parenthesis with this absolute value. There we go. There we go. It just wanted a parenthesis. Now it's happy. So there's my function. Now, what I just did is I graphed what I think the antiderivative is. And if this is the antiderivative, then the derivative of this thing in the box should equal the integrand. So if I type the integrand in here, it should be the same as f prime. So I'm going to put 3x minus 4 over x squared minus 5x minus 14, and then see if my green graph and my purple graph are the same. Now, I did that kind of quick with some annoying parenthesis issues in the way, so let me explain again. When you take an antiderivative, the whole point of taking the antiderivative is I want something, this thing in the box, whose derivative equals the integrand. So I want the derivative of the box to equal the integrand. So what I put into Desmos is I put in f of x being the antiderivative I got, f prime of x being the derivative of the antiderivative, and then the integrand, and then I just checked to make sure that these two things were the same. So, fun way to check your answer. Yay! Okay, so now in example 2, slightly more complex, but not in like a scary way. We're going to do the same thing, but this time you got to remember to divide by a lead coefficient. Let's do it. All right. So I have 5 over 6x squared plus 11x minus 10. So this is going to be probably 3x and 2x. I need to get 11 here. And so 10 is going to be, let's see, 5 times 2. And that will work. Plus 5 will give me 15. Minus 2 would give me minus 4. 15 minus 4 is 11. So a over 3x minus 2 plus b over 2x plus 5 equals 5 over what I have. Now, I showed you how to get the common denominator last time. If you want to do a lot of that in your head, by all means. So I know that a is going to get multiplied by 2x plus 5. I know that b is going to get multiplied by 3x minus 2. And I know that that sum of those products needs to equal 5. So I have 2ax's plus 5a plus 3bx's minus 2b equals 5. So 2ax's plus 3bx's equals no x's whatsoever. And 5a minus 2b needs to equal 5. Again, this is stacked up pretty nicely, so I'm going to multiply this numerator by 5. Not numerator, why did I say that? The top equation by 5 and the bottom equation by -2, which is going to give me 10a plus 15b equals 0. Negative 10a plus 4b equals -10. So 19b equals -10, making b -10/19. Okay? And then I need to find a, so 2a plus 3b needs to equal 0. So then 2a equals 30/19. So a is 15/19. They're fractions. They're not whole numbers. It's fine. We're fine. Now I need to break my original apart. So this original integral, this original rational expression can be broken down into 15/19 over 3x minus 2 plus -10/19 over 2x plus 5 dx. And the antiderivative of 15/19 over 3x minus 2 is going to be 15/19 ln absolute value 3x minus 2 divided by 3, because the derivative of 3x minus 2 would be 3. So when I take the antiderivative, I have to divide by 3. Okay, it's really a backwards chain rule. And then the same thing over here. I'm going to have -10/19 ln 2x plus 5, but the derivative of 2x plus 5 is 2. So I got to multiply by 1/2 when I take the antiderivative, plus c. So really, I have 5/19 ln 3x minus 2 plus -5/19 ln 2x plus 5 plus c, and those have the same coefficient, so that's really 5/19 ln 3x minus 2 over 2x plus 5. Hooray for log laws, because if I'm subtracting, I can divide. Woohoo! Now, I did all this while making a video without the answer key next to me, so let's check to see if I got the right answer. And goodness gracious sakes, do I really hope I did. So if I go back and do my Desmos thing again, the nice thing is I've already got it set up. So 15/19, 3x minus 2 over 2x plus 5. So we're going to take this and say I have 15/19, right? Was it, no, not 15, 5/19. ln parenthesis absolute value da, 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 3x minus 2 over 2x plus 5. Okay, so the derivative of that, okay, is going to be the thing in green. And I want that thing in green to match my original rational expression, 5 over 6x squared plus 11x minus 10. Green, purple, green, purple. They match. The derivative of my antiderivative equals the integrand, which is exactly what I wanted to happen. Hooray! So there are two of our basic advanced partial fractions. Okay, that's partial fractions in a nutshell. Now, we're going to do one more in this video, and then I'm going to start another video for what happens when we have three linear factors. So one more together. Example 3, divide first. Well, why do I have to divide first? Oh, because that numerator is not linear or a constant. It's a quartic. So what I need to do here is I need to divide it out first. So if I have to divide that out first, we're going to do long division of polynomials. All right, so 3x to the fourth plus 1 over x squared minus 1. So I got to divide long division of polynomials. 3x to the fourth plus 0x cubed plus 0x squared plus 0x plus 1 is going to get divided by x squared plus 0x minus 1. All right, so x squared times 3x squared would get me 3x to the fourth. Distribute that 3x squared to my divisor, and then subtract. 3x to the fourth minus 3x to the fourth equals 0. 0x cubed minus 0x cubed equals 0. 0x squared minus negative 3x squared is positive 3x squared. And then because I eliminated the first two values, I can bring down two values. And then x squared times 3 is going to give me 3x squared plus 0x minus 3. Subtract. 3x squared minus 3x squared is 0. 0x minus 0x, 0. 1 minus negative 3 is 4. So this is 3x squared plus 3 with a remainder of 4. Well, what does that mean? That means that this can be rewritten as 3x squared plus 3 plus 4 over x squared minus 1. Okay, and then I have a dx there. Fantastic. Okay. Well, I can take the antiderivative of 3x squared plus 3. I can try to take the antiderivative of 4 over x squared minus 1, but that's going to require partial fractions. So I'm going to separate this into the two pieces I know I can handle. 3x squared plus 3 dx and 4 over x squared minus 1 dx. Now, you don't need to separate these, but I'm going to just to remind you that I can just add 1 to the power, divide by the new power, and just handle that on my own, and then come over here and deal with the partial fraction later. So I have a over x minus 1 plus b over x plus 1 equals 4 over x squared minus 1. So ax plus a plus bx minus b equals 4, meaning a plus b x's for 0 x's, and a minus b equals 4. I'm going to add those two equations, so 2a equals 4, a equals 2, and if a plus b has to equal 0, b is negative 2. So then this is the integral of 2 over x minus 1 plus negative 2 over x plus 1 dx, which becomes 2 ln x minus 1 minus 2 ln x plus 1, which becomes 2 ln x minus 1 divided by x plus 1, that when I combine with this thing up here, I get a final answer of x cubed plus 3x plus 2 ln x minus 1 over x plus 1 plus c. Whew! There was a lot going on there, so I definitely want to check this thing. All right, Desmos. Desmos to the rescue. X cubed plus 3x plus 2 that. All right, so x cubed plus 3x plus 2 ln, and then it was x minus 1 over x plus 1. So there's my antiderivative. There's the derivative of my antiderivative. And I want that to equal the original fraction that was in the integrand, which who even remembers at this point what that was? 3x to the fourth plus 1. 3x to the fourth plus 1 over x squared minus 1. Green, purple, green, purple. And look, they're the same. Yay! We did it right. You don't have to go back and fix anything. Yay! All right. So, friends, there is partial fractions part 1. Come back for more fun in partial fractions part 2.